Rocks formed from magma are called igneous rocks and contain a lot of useful information about tectonic, magmatic, and volcanic conditions on Earth. To better understand how magmas form and evolve, we need to discuss things like the geothermal gradient and other processes and how they relate to some of Earth's main plate tectonic settings. Shown here is a typical eruption of magma at an active volcano. This diagram of the rock cycle shows the three major rock types and how they are related by various processes. Igneous rocks are the primary rock type, forming as magmas cool and crystallize either at depth or on the surface. Several factors determine how an igneous rock forms, but the depth environment is probably the most important. Magmas that cool and crystallize at depth form what we call plutonic igneous rocks, also called intrusive igneous rocks. Igneous magmas that erupt onto the surface are termed volcanic igneous rocks, or extrusive igneous rocks. Before we talk about all the different types of igneous rocks, these notes will describe how and where magmas form and evolve. So, how do magmas form in the first place? Well, the Earth still has abundant heat trapped within its interior. This heat has several sources, including the heat of formation from when the planet originally formed over 4 billion years ago, the heat of radioactive decay of various elements within the Earth, and the heat from tidal stretching due to the gravitational forces between the Earth and the Moon. This heat is slowly making its way to the surface via various processes. Heat can travel fairly quickly by convection in the liquid outer core and in the mantle. Heat can also travel much more slowly, molecule by molecule, by the process of conduction. We can draw a simple illustration to show how temperature changes with depth. We can call this a DT diagram, or depth temperature diagram, with temperature on the horizontal axis and depth on the vertical axis. Pressure increases proportionally with depth, so we could also show pressure on the vertical axis. This would make the diagram a PT diagram. The temperature and pressure on the Earth's surface are marked by the yellow circle. Progressing downward into the Earth from that point, the temperature rises, slowly increasing the deeper you go. This is shown by the green line, otherwise known as the geothermal gradient. For any given geologic area, the geothermal gradient defines the temperature profile with depth. Not only does it get hotter with depth, but the pressure increases as well. The increasing pressure with depth typically keeps rocks from melting. Thus, rocks of the Earth's crust and mantle might be really hot, but they're still solid due to the extreme pressure. Different geologic areas may have different geothermal gradients. Let's look at a simple example. Here's our DT diagram with two different geothermal gradients from two different areas. Geothermal gradient A shows an increase in temperature from 0 degrees to 1,000 degrees at 50 kilometers depth, and equals a gradient of 20 degrees C per kilometer. This colder geothermal gradient is indicative of a continental interior or an area away from any major active volcanism. Geothermal gradient B increases to 1,000 degrees C in 25 kilometers depth, so its geothermal gradient is 40 degrees C. This hotter geothermal gradient is representative of active volcanic areas. Well, solid rock will start to melt once a certain temperature is reached and the bonds between atoms start to break. This temperature is known as the solidus and represents the highest temperature at which a rock is completely solid. Let's look at the depth temperature diagram again. And so the area within the Earth that is solid rock is shown here. Here is the Earth's surface. And the geothermal gradient describes the increase in temperature with depth, getting hotter and hotter the deeper you go, until a certain point is reached where the rock is so hot it starts to melt. And this is called the solidus. Solidus is the highest temperature at any given depth at which the rock is still completely solid. partial melting takes place above this temperature and magma is created, and we call that partial melt. Partial melting starts with the minerals that have the lowest melting temperature and proceeds as long as there is sufficient heat. Partial melting is just what it says. Only part of the original rock melts, maybe 1%, 2%, 5%, 10%. You can get melting as high as 30% in some cases, but you're never really melting the whole volume of rock. So that's why it's called partial melting. Note that the orange solidus line is not vertical. This is because the melting temperature increases with depth. Remember, as pressure increases with depth, so must the temperature necessary to start melting the rock. To the left of the solidus line, the rocks are still solid, but to the right of the solidus line, partial melting occurs and magma begins to form. So the point where the geothermal gradient intersects the solidus line is that depth and temperature where magma first starts to form. The position of the solidus on a depth temperature diagram is controlled by rock composition. For instance, in this depth temperature diagram, the orange solidus is for the rock type gabbro. It represents those depths and temperatures at which gabbro is solid and where it isn't. If another rock contains different minerals that, say, melt at lower temperatures than gabbro, it will have a different solidus line. One example would be the rock type granite. And this would be the solidus for granite because it has a number of different minerals that melt at lower temperatures than ones in gabbro. So, what factors are important in the melting of solid rock? Well, there are a number of ways in which solid rock can melt, but the most obvious would be to increase its temperature. We've seen that partial melting can occur when a rock is heated above its solidus. This diagram shows this situation with the geothermal gradient passing through the solidus and partial melting occurring. Consider a rock at position X on the geothermal gradient. Simply increasing the temperature on this rock will eventually cause it to reach its solidus temperature, and if it exceeds the solidus temperature, will start to melt. Solid rock can also partially melt by significantly decreasing the pressure, typically by uplifting the rock to more shallow, low-pressure depths and conditions. Consider the rock at position Y on the geothermal gradient. It is very close to its solidus temperature already, but it's still in the solid field. So simply decreasing the pressure on that rock will eventually cause it to reach its solidus and pass through, causing partial melting, with no increase in temperature necessary. This is known as decompression melting, which is a very important magmatic process at mid-ocean ridges, intraplate hotspots, mantle plumes, etc. The temperature at which a rock will melt is also controlled by the presence or absence of water, which has the effect of changing the position of the solidus, effectively lowering the melting temperature of the rock, making it easier to melt. Thus, the solidus line for a rock under hydrous or water-rich conditions will be different than for the same composition under anhydrous or dry conditions. Under anhydrous conditions, this is the solidus line for the rock type gabbro. So a gabbro at position Z1 on the geothermal gradient will be solid because it's to the left of the solidus. However, under hydrous conditions, the position and shape of the solidus is changed so that the same gabbro at position Z1 will now be experiencing partial melting, as it's to the right of the solidus. A gabbro at position Z2 on the geothermal gradient will still be solid, but the presence of water has changed the solidus and lowered the amount of temperature increase necessary to melt that rock as compared to anhydrous conditions. Hydrous melting is a very important process in plate tectonic settings like subduction zones, and the presence of water is a major factor in the explosivity of volcanic eruptions. Let's talk about 3 different groups of plate tectonic settings where magmatism occurs. The first group includes divergent margins like mid-ocean ridges and continental rifts. In both cases, hot mantle rock rises and partially melts due to decompression melting beneath the tectonic plates that are diverging or pulling apart. This is how oceanic crust forms at mid-ocean ridges like the Mid-Atlantic Ridge, the East Pacific Rise, the Red Sea Rift, and others. This decompression melting process also occurs at spreading continental plates like the East Africa Rift. Intraplate hotspot magmatism occurs where hot mantle rock rises within what is called a mantle plume. As the pressure decreases, the top of the plume expands and decompression melting occurs. The resulting magmas produce intense heat that can melt the overlying lithosphere, whether it's oceanic or continental. The location of any related volcanism above the mantle plume is called a hotspot. One hotspot located near the middle of the Pacific Oceanic Plate is the Hawaiian hotspot, and a hotspot located on the North American Continental Plate is the Yellowstone hotspot. The Big Island of Hawaii is the largest and easternmost volcanic island in the Hawaiian hotspot chain. Current magmatic activity is greatest in the area of Kilauea and the East Rift Zone. And 35 kilometers off the southeast coast, there's Leighty, the newest Hawaiian seamount. At around 3,200 feet depth, Leighty is projected to break the surface in 10,000 to 100,000 years, when it will become the newest Hawaiian island. If we zoom out and look northwest along the Hawaiian island chain, we can see the main islands. And as we go, they grow smaller and lower. And eventually, we will reach the last of the islands, Midway and Curie atolls, which are reef complexes situated atop broad flat-top seamounts. Beyond this point, only seamounts record the trace of the Hawaiian hotspot. The active caldera above the Yellowstone hotspot is not readily apparent in this view. But when we zoom out, we can see more clearly its path forged across the western U.S. over the last 15 million years or so. Magmatism is also common at convergent margins, where an oceanic plate subducts beneath either a continental plate or another oceanic plate. Subduction zone magmatism typically originates with hydrous melting above the downgoing oceanic slab. Melting of water-rich minerals within and above the subducting plate form magmas that rise and create a line of volcanoes, or volcanic arc, on the overriding plate. The water-rich magma also tends to create explosive volcanic eruptions. Subduction zone melting is a major process in how continental crust is formed as well. Examples of convergent margins include the Andes Mountains in South America, the Cascade Mountains in North America, the Japanese islands, etc. Looking north along the south-central Andes, we find a multitude of active stratovolcanoes that form the Andean continental volcanic arc. One of them is Villarica. Villarica is one of Chile's most active stratovolcanoes, with recorded eruptions going back to the 1500s. And this is Mount Hood, located roughly 50 miles east of Portland. From here, you can look north along the Cascades continental volcanic arc. There's Mount Adams, Mount Rainier, Mount St. Helens, the Portland area, and as we look to the south, there's Mount Jefferson, and eventually Three Sisters in the distance. So, what happens once a magma is formed? First of all, it will start to rise due to its buoyancy contrast with the surrounding rock. This process is similar to the workings of a lava lamp, with the rising of hotter, lower density material. Note that technically it should be called a magma lamp. But anyway, magmas may take on many shapes, but diapirs are very common. Diapir, not diaper. Okay, and a diapir is simply a bulbous shape with a larger head and a more slender tail. So magma diapir is a common term you might run into. And magma sources can be in the mantle or crust. It can be deep within the mantle, 100 kilometers or more deep in the mantle, or it could be in the crust at more shallow levels, just a few kilometers. Once a magma forms and begins to rise, it may experience change due to one or more differentiation processes. These typically alter the magma from its original composition. It's relatively rare for a magma to erupt at the Earth's surface with the same composition as the one it started as. There are many ways in which a magma can experience differentiation. The magma itself can cool and crystals can start to form. This crystal fractionation removes some of the early formed, more dense crystals, and they start to fall out towards the bottom of the magma chamber, leaving a slightly less dense magma behind. The magma might interact with the surrounding country rock. It could bake it and actually partially melt it and assimilate it. You can have pieces of the country rock falling into the magma chamber. There's a number of different processes going on, and it can be quite complicated. But the bottom line is, the magma leaving the magma chamber may or may not be similar to the magma that entered the magma chamber to begin with. Sometimes magmas may mix together, and if they have different compositions, this can cause contamination to each magma. This magma mixing process can result in the creation of new hybrid magmas. For example, mixing of a mafic magma with a felsic magma, like mixing chocolate and vanilla, may produce a composition somewhere in between the two, typically known as intermediate. As magma moves upward, it may interact with the surrounding wall rock or country rock, and may result in the contamination of the magma. As the magma works its way into cracks and fissures, fragments of the wall rock may be incorporated into the magma. These fragments have many names, but are commonly called xenoliths, which means foreign rock. If the temperature of the magma is higher than the melting point of the wall rock material, the wall rock will start to melt and begin to assimilate within the magma. This assimilation process usually results in the contamination of the magma and ultimately changes its composition. The degree of contamination depends on the temperature of the magma, the composition of the wall rock, and other factors. As magmas rise, they inevitably cool, allowing crystals to form. Depending on the magma's original composition, crystallization of certain minerals occurs across a range of temperatures. For example, in a mafic magma, minerals like olivine and calcium-rich plagioclase feldspar will crystallize from the magma first, followed by other minerals at lower temperatures. Typically, early formed crystals are more rich in iron and magnesium and calcium, and will tend to sink and plate out in layers on the bottom of the magma chamber. This process is called crystal settling. Additionally, elements in the crystals like iron, magnesium, and calcium are thus removed from the liquid magma, so the remaining magma becomes depleted in these elements. This is known as crystal fractionation, and the composition of the magma continually evolves during this process. Well, that's all for now. Till next time.